Oh, thank you so much. Today I'm gonna share my thought process about weak lensing and that I'm using as a probe to measure dark matter or the galaxies. So dark matter, as we all know about dark matter, it is composed like it takes around 25% of the word, but still we don't know what it is. We don't know the nature of dark matter. So to measure this dark matter, we have a view that we have a galaxy that is luminous, which is composed of gas, dust, and stars, which is surrounded by a dark matter, as you can see in this image. And this luminous matter actually emits or reflects the light, so we can see it, but dark matter we can't. However, this dark matter plays a important role to form information and structure of the galaxy. And weak lensing is one of the probe. I mean, we have a lot of probes to measure the dark matter, but weak lensing is one of them. And what is weak lensing? As you can see on the left hand side, when we have a source like background uh, galaxy or foreground galaxy, which is aligned in a line to the observer, then we see that the background galaxy image actually is distorted. And as you can see in the left hand side image, in the blue box, you can see the source. We call it background image, background galaxy as a source. It actually is stretched and is distorted. So this is a effect of weak lensing. On right hand side, you can see in a more larger view. So as you can see, the center, which is yellowish, is a lens, and the shaded gray is a dark matter, which has caused the distortion to the background images, that background sources, which is shown blue, in blue shapes, which has been distorted. But in weak lensing regime, it is actually highly uh, possible that we can't see whether galaxies has actually distorted or not, because this effect is very small. So, and we know that galaxy comes in different sizes and shapes. So, how we measure this distortion that we call as shear, this elongation, we call it shear. How we measure this? In weak lensing, what we do, we actually measure a lot of background sources from the same sort from the same lens, and then uh, sorry, and then we just average them out and consider that the averaged shape of those galaxies is circular. And then that's how we measure this as a distortion parameter or shear in weak lensing. Now, let's consider this in a a slightly different way. What we call it precision weak lensing. How? So in precision weak lensing, instead of considering that we have circular shape, we consider that we have a circular velocity field for our source. What that means? It means that our major and minor axes are orthogonal. And as in the same way that a shape is distorted, we consider that the circular velocity of our source is also distorted. So when we had lensing effect, is orthogonality of this axis, major and minor axis, is actually break. So we got this shear measurement from here. This method is actually proposed by Blaine and Morales. Uh, Blaine said that under the lensing effect, the photometric and kinematic axes are not same. And when they are not in lensing effect, they are same, like they are orthogonal. And Morales said that their axes are gonna break. So we are combining both of these them and got our new method, we call it precision weak lensing. And in 2020, Paul Guri has measured this first measurements using precision weak lensing, which says that this method is 10 times better than the conventional weak lensing. I'm calling weak lensing as a conventional weak lensing. But here is the problem that Guri just used a very small data sample, was 18 galaxy system, and also he has only used one source per lens, so we don't know how accurate it is, but it is peer reviewed, so we completely trust, and we said okay, it works. Now my work is to get the dark matter measurements for a galaxy. So what I'm using this methodology, and I'm trying to get this dark matters around a galaxy, uh, how tightly I can constrain that. For that, what we need, of course, we need a lot of data. So I have observed data from AAT telescope, WIFE's data, which is 2.3-meter telescope, and I use Keck then, where I'm using DEMOS, and then I'm using AAT Koala, which is 3.9-meter telescope. And how it's gonna look like in a pictorial way. So we have one source galaxy from Guri. As you can see here, is one source for Guri sample. Then we measured from DEMOS. We have a lot of sources from DEMOS we observed here, and then I'm using Koala to observe the galaxy, so I can constrain the innermost dark matter for this lens. Till now, I have observed around 53 nights, and there are a lot of samples now, and still this is an ongoing process. Now we have used DEMOS data, so we can have so many sources, and using these sources, we can enhance our shear measurements. For DEMOS, this is my one of the galaxy that I have observed. This is a slit mask data. So you can see it is NGC 151 where I have observed these sources. And now you can say that, okay, with DEMOS, you have so many samples for sources, but still, when you have slit, you have limited signal because of slit, and you are using velocity field. So you are gonna lose those uh, data because of slit. But I'm gonna answer this, how we have tackled this problem. But before, we have got reduction from pipette pipeline, and then we have extracted sources, and then after that we have estimated redshift for our sources. Look how beautifully it actually fit and got the redshift for our sources. Now, question is how we have tackled this limited signal problem. So we have used our DEMOS mask in such a way that we have observed our sources at three observations with 1 arc second with the width of slit, and we have used that slit, so we can uh, put slit over slit with a small offset like 1 arc second of the width, and then using our fitting and getting after this fitting, we just fit H alpha and N2 and got the velocity field. This is the example of our one of the source velocity field that we got from DEMOS data. After getting this velocity field for our sources, we have used like we first time we are using it as a multi-object IFU, and we have used this velocity field to get our shear estimation. And from this shear estimation, we can also go for the hollow mass estimations. But for now, I'm at the stage where I'm getting the shear estimations from these velocity fields. Now, for our koala and wife data that we have observed lenses, we are using dynamic modeling that Michael Capillary has given us, a beautiful one. So this is our GC151 again, there where I have run a gem modeling, and we fit this multi-Gaussian things. So we got this surface brightness. You can see on the left hand side that galaxy has given in the yellow denote the higher brightness region. And in the center, I just gave the image of NGC 151, so you can see how image looks like and what we are getting. On the right hand side, it gives the model that has helped us to predict the brightness of this galaxy. And then we have run our gem modeling on that, but here I just made a mistake when I was running that. So I ran another galaxy, and I didn't realize. Also, I have used their surface brightness, and this is another galaxy. So we ran our gem modeling on that, and from that we can get stellar mass to light ratio and dark matter fraction. This is our gem modeling thing. Next step would be to get hollow mass using our lensing measurement using shear. And then afterwards, we can combine these dynamical and lensing mass to get the detailed hollow mass constraint on that. And future ongoing survey, because I'm having a lot more nights to go on. So we are observing not just between 10 to 100 kpc, because until now I have just used the 10 to 100 kpc distance between lens and sources. Now we are going much closer to the lens, and we are using around 5 kpc and even 4 kpc sources. So here's an example for that. And last month I just thought about that why not we can also use strong lensing to constrain this. So we are also observing our strong lensing galaxies like this. We have this strong lensing from this literature, and we can go for weak lensing stuff for this strong lensing galaxy. Now, in my mind and in thought process, I can just see that we can have these science cases for things, and I will be happy to discuss if anyone say that there are other more science cases and they think there is some problem with these science cases. There is some things that you can't do with these things, and anything, whatever they have in their mind, I would like to discuss. And anyone wants to collaborate with us, I'm very, very happy to do that. That's it. Thank you.